So, thank you, Perman. So I'm Francesco, founder and technical director at Erlang Solutions. I've been working with Erlang. I've been privileged enough to be working with Erlang since the mid-90s, and I think that was, that's allowed me to actually see a programming language become an ecosystem of languages. On the side, in my spare time, I ended up writing 2 of the main titles, which came out with O'Reilly. And also, in my spare time, I teach at Oxford University the concurrency-oriented programming course for the master's students.
Okay, so I'm Robert. Hello, Robert. Thank you. Sorry, that's a joke. So I used to work at Ericsson in their computer science lab, and I was one of the 3, together with Joe and Mike, who did the initial development of the Erlang language. I now work for Erlang Solutions. Principal language expert. I did not devise that
I did, yeah.
title. Yeah. I mainly work with training and doing some consulting as well too.
Well, hello, Robert.
Hello, Francesco.
And this is not working.
Wait, you have to do this. Now try it. Now
and hello, Joe. Yes.
Yes.
So what we're looking at is concurrency-oriented programming, and this was a term which was coined by Joe Armstrong. At least, that's searching around, that's what we found. A previous term I found was concurrency-oriented object-oriented programming, which was not quite it, but yeah, there might be a link. And it was first used during his opening keynote at the MIT Lightweight Languages Workshop in 2002. Paul Graham at the time was the chair. I recall Joe coming back really enthusiastic about it, trying to explain to Ruby Mats and trying to convince him to add distribution to Ruby, the language. And back then, no one knew what Erlang was. No one knew who Joe Armstrong was. So I think it was really, really big. And in his talk, he actually introduced his tenets. His tenets, if you've not heard the term before, is a principle or a belief. And we actually need to chase up the program chair because the videos which was there are no longer accessible. I don't know if they've put them on YouTube. But it was a really interesting talk, again, probably ahead of its time. And there he went in and explained that the world is concurrent. So think of as every one of you in this room as an independent actor, and it's an independent process. Things in the world don't share data, so we don't share brains, we don't share. We each store a copy of the data we deem is necessary.
I can just say, Francesco, that depends which science fiction books you read, but never mind. We go with the ones we don't share.
And things communicate through message passing. So right now I'm broadcasting a message to all of you. I'm doing it asynchronously. And you take on board the message I'm sending you, and you decide what to keep, what's relevant to you, and what's irrelevant, and chuck away. And, well, we're in London. I don't live in London anymore, so the first rule, if you are coming from outside London or outside the UK, when you cross the road, is look both sides before crossing. And because, obviously, I don't know how many tourists get hit by a bus when they look right and the bus hits them from the left. Point is, things fail. And when things fail, sometimes they do recover, sometimes they don't. But based on these principles, how do you actually go in and design a programming language? And that's exactly what Joe, Mike, and Robert did.
Yeah, so one of the things the computer science lab at Ericsson were looking at is how could they improve the programming of their telecom systems. So they were very successful, but they were difficult and costly to maintain and to manage and program. So we started looking, and we went through a large number of languages we could run and test. We did test against real systems the whole time, and we found that no language really suited us. So we started looking at developing a language for doing this. I can say now, we didn't start off, didn't have goals of making it functional. We didn't have a goal of making it obey the actor model. We were looking at the problem and how we thought would be the best way to solve the problem. I mean, there's a lot of concurrency in telecom systems. There's a lot of necessity for fault tolerance and things like this for it. So we started looking at that. And we were very...
I don't think you weren't even looking to inventing a programming language.
Well, it just happened. We were looking at programming the system up. The initial system was actually done in a Prolog system, talking with it, and we were modifying the system around that Prolog to do it, and the language modified as we went and developed, etc. If you look at if you look at the old movie, I'm sitting in front of a screen. Joe and Mike, they're just talking, right? I'm that one actually fixing it. If you look at that syntax, it's the old syntax. It won't run today. But anyway, we're looking at this thing, and we felt that nothing really worked out, and what we found was so important was things like the concurrency, the processes, the error handling. These were so fundamental things to the problem that were not something you put in a library on top of it, you put them in the language, right? And the whole language development was extremely pragmatic. We had a user group who were using it, and they were testing this to make a prototype for market architecture, and they came back with feedback on ideas of the language and how you use these properties. So it came with comments and feedback and said, yes, this idea works. This is great, this is fantastic. This is a fantastic idea, but we can't use it anyway, right? Type of thing. And this is bad. So the whole language evolved extremely pragmatically. And as I said, it became functional along the way. It became implementing the actor model along the way. Yeah, that's me working, right? That's me working, seriously. So we were going to an IT show in '93, and we wanted to show Erlang, display Erlang. And we thought, how can we get people to come and look and listen to us, what we're saying? And we had a small exchange. This thing here, that's a small business exchange we had in the lab, which we were using to do all our tests. And we thought no one would come and want to look at that, right? It doesn't even have blinking lights, right? So we thought, maybe a little train set. So we started implementing a train set and implementing a train control system in Erlang. And I will freely admit I went slightly overboard. Okay, for this. This was not the board that was being used, but we had an automatic train control system. We had blocks in the track. You could detect when trains were in the blocks. You could stop trains from coming to avoid collisions. You could program, give the train a path to go through, and the whole thing. The ATC system would control this for you, do everything for you. It even had a fail-safe system. So sometimes happened there were magnetic sensors, and sometimes the train wouldn't be able to trigger that sensor. So the system would think it's in the wrong place, and something was going wrong, and then it just stopped everything. So we never had a collision, right? But it was fun. It worked, yes.
Yeah, concurrency and fault tolerant at its best. So going back, I mean, the main building block, now we're talking about Erlang here, but we're referring to any language in the ecosystem. So the syntax here is actually Elixir. But the main building block, which you tend to work with when you work in the ecosystem, is a process. And they decided very, very early on to decouple the concurrency model from that of the underlying operating system. I mean, these were the days where you could have a maximum of 16 threads per machine. And so they had to use a virtual machine to go in and achieve concurrency at scale. The concurrency at scale, I think back then, I think when I started, it was maybe 10, 15,000 processes, went up to around 30,000, I think, which the VM could handle in the mid-90s. And then, we'll see very soon to where it got to. But it's, and even today, I mean, looking back, you still can't use OS threads, even though they scale much more, as lightweight processes. If you look at the Beam VM, to create a process will take microseconds, and they will utilize just a few bytes of memory. Obviously, that allocation will increase as needed.
So yeah, the basic concept is a process. So we here that spawns a process, and we're spawning a process running the function print_add, which just adds two numbers together and prints them out, right? But when the process the code the process has been started with ends, the process dies. Okay, there's nothing more for it to do, so it just terminates and dies. And in this case, because it's not crashing or doing anything strange, it's dying normally, right? And here, we're starting another process. We're going to run the function in kaboom in foo, and that's going to divide 1 by 0. And that's going to cause an error. And when an error occurs in a process, the process terminates, it crashes, right? So we're very strict on that. And once a process dies, everything about that process goes away. There's nothing left of that process at all, anywhere. How do we communicate? We send messages. there's a send here, we have a PID, the process identifier, we can send a message to it. That's asynchronous. It will eventually arrive at the process sometime. So it's very, getting back to what you were talking to yesterday, it's quite close in many ways, right?
So for those of you who saw Vagiv's talk yesterday, this is the very construct he actually went in and described. It's asynchronous message passing, and it's at the most one semantics. You send a message, but you've got no guarantee that the receiving process will receive it, for the simple reason that the receiving process might have terminated or might have crashed. And this is something I think we've realized, how do you handle this failure? It's something you need to do in the business logic of your system. It's not something you can abstract or automate or look away, because every system behaves differently. Every message in a system needs to be handled differently. And so you send a message, but you've got no guarantees that it has been received. If you do need those guarantees, you need to put libraries on top of it, or frameworks, and through that, you can create synchronous message passing. You send a message, and then you wait until you receive a response. You can send a message and wait, and if you don't receive a response, you can send a message to another process. So you can start using different types of patterns, but we tend to use that, and we've always done that, and handled them in the business logic itself. And so Vagiv's talk, I think, was very interesting, seeing how he came to that realization that you needed to do it in the business logic, and I think we came to very, very similar conclusions as he did. Now, messages which are sent are actually received in a mailbox, so they're stored in a mailbox, and whenever a process executes in a receive clause, the mailbox is scanned sequentially. So messages are just stored, and when the process is ready to retrieve them, they're scanned, and we go in and can do a selective receive. So we can decide exactly which messages we leave in the mailbox and which messages we extract from the mailbox. And you might think, this is, why not receive them and handle them in the order in which they arrive? This is very important when you're, for example, doing things such as finite state machines where messages come out of sequence. It really simplifies the task of doing them, because if a message comes out of sequence, you just don't match it. You don't extract it. You just leave it in the mailbox until in the FSM you reach a state where you can handle it. So these are the building blocks, and it actually simplifies the overall code base when you're doing it.
I can also make a comment. Having the selective receive means you can avoid a combinatorial explosion. Otherwise, in principle, you should be, if you had to receive every message everywhere, you would have to handle every message that could come to this process everywhere. And you might have hundreds of thousands or thousands of messages that are being sent around processes. Here I can be extremely selective. I'm interested in this message. Anyone else, I'll just leave it for someone else. Right?
Yeah. So this is how we do failure detection in Erlang. What we do is we've got two processes, and processes can link to each other. And I think this failure detection is the actual reason as to why Erlang became concurrent. They realized that in order to detect that something had gone wrong, you needed something else to detect it. So to detect that a process had crashed, you needed another process. And this reminds me of a similar story where Mike Williams, one of the three co-inventors, worked on the very, very first mobile phone systems. So this was a time when a mobile phone could only call another mobile phone. And the way that they support these systems and make sure that that there was, I don't know how many nines uptime it was, but it was basically they had a human sitting in front of a screen, and as soon as the text started scrolling very, very fast, they knew the system had crashed, and manually they'd go in and restart it. And so in a way, that human looking at that screen was a process. The system he was looking at was another process. And that's how they dealt with it. And that's how they, I think, came to the realization that at least, you needed at least two of everything to make a reliable system.
Yeah.
And then okay, we're dealing with phone calls. There are thousands of phone calls happening at any one point in time. That's how they expanded. So this, this failure mechanism, this looking at a screen, was recreated for process links. And
so what happens is that when two processes link together, when a process dies, crashes, for example, the PID1 here, it sends an exit signal to all the processes it's linked to. That's just a basic underlying mechanism. And when that happens, when the signal reaches PID2 here, that will crash it. Next slide.
Yep.
That will crash that PID. So that means all the processes are linked together. One crashes, they all crash, which means you can take down a lot of processes cooperating and working together. This is the base of the Erlang let it crash principle. Right? We just let processes crash because we know that the system is built in such a way that other processes will detect the processes crashing and know what to do when that happens. Right? And yeah.
So yeah, I mean processes, obviously we don't want processes crashing all the time. We want to detect that something's gone wrong. And by the way, a process crashes when maybe the state becomes corrupt or there's a bug in your code.
Yeah, and kaboom from
kaboom, yes. Or you basically let it terminate abnormally.
Yeah.
And so this is detected by processes which, what we denominate, processes which are trapping exit. We usually have removed the double circle. And what happens is if a process is linked, which is trapping exit, is linked to a process which terminates abnormally, an exit signal, which is sent to the process, is actually converted to a message, and this message of the format exit PID reason is stored in the mailbox with all the other messages. And again, when going into a receive clause, it can be selectively received. The process which received it notices, oh, something's going wrong with this process. It could potentially go in and restart it, or it could decide to terminate itself, or not do anything. So it makes that decision over how to go in and manage and handle it. And also, when an exit signal is caught, it no longer propagates to other processes. So if PID1 is linked to PID2, PID2 is linked to PID3. If PID2 catches the exit signal, PID3 continues executing and nothing happens.
Yeah. This can be used for monitoring processes and knowing what to clean up about after them. So processes have allocated resources. If they terminate and crash, then the resource handler will detect this and know how to clean up for them. We can also use things we have processes we call supervisors who are monitoring their child processes. And if a child process dies, the supervisor knows what to do. Do I restart the child or not? Maybe depending on how terminated, things like this for it. Maybe I want to kill off all my children and restart them all because we know they're all linked together. But this is the supervisor's job of doing that. It's not my job when I crash. My supervisor will know what to do. This is how we can make truly fault-tolerant systems, because the process crashing might be service providers that just have to be in the system for the system to run. And they will have a supervisor, and if and when they die, then the supervisor will know, I have to restart this, and we'll do that.
Yeah. But I'd say none of this is new. Think of Smalltalk. In Smalltalk, you've got objects. Objects don't share memory. And surprise, surprise, objects communicate with each other through message passing. And yeah, this is a quote from Alan Kay, which Joe Armstrong was very glad to discover. Alan Kay coined the term object-oriented programming. And this is the quote Joe Armstrong used when saying, Erlang might be the only object-oriented language because it was based on message passing. You've got isolation between objects, and you have polymorphism. And he said this with a bit of tongue-in-cheek, of course. Not everyone agrees. But it got him to go out and basically tell the world Erlang is the only pure object-oriented language out there. It's
not everyone agrees with that.
But why is this relevant today? Why are we here on stage today? I mean, this is stuff which happened in the 90s. Today's systems are all distributed. Mobile phone, it's your apps are a distributed system connecting to a server. Systems running in the cloud, running in the edge, IoT networks, IoT devices. Any system connected to the internet today has to be both scalable and reliable. There's no getting out of it. And we've got a concurrency model here based on no shared memory. And this is basically key to distribution. Because if you've got two processes, it doesn't matter if you place them on separate machines, because you don't have the problem of where you place your shared memory. They each have a copy of the data, so if you get a network partition between these two machines, they can still continue running independently. So, once you have the distribution, you can actually go in and distribute your processes, and the state, of course, for scale, or you can actually copy your processes and their states for resilience, because if one machine fails, the other machines takes over. And these are basically concurrency models based on no shared memory and message passing, which give you both. And not only, if you go in and add multi-core, you get parallelism into the mix as well. And this became really, really evident in, I think, 2018, when I went in and managed to get Carl Hewitt, Joe Armstrong, and Tony Hoare on the same sofa in a discussion, a panel discussion, and an interview. And what I asked them was, what problem were you trying to solve? And I started with Carl Hewitt. I think I started with Joe Armstrong. What problem were you trying to solve when you co-invented Erlang? And he replied, I was trying to figure out how to build fault-tolerant systems. I asked Carl Hewitt the same question. I was trying to figure out, so Carl Hewitt invented the actor model. And he went in, I was trying to figure out how to program distributed systems. And went in and asked Tony Hoare that question. I was trying to figure out how to program transputers. So things which seem very different, but which are very, very much connected to each other. Because you've got concurrency with no shared memory. That gives you distribution. Once you have distribution, you've got scalability and reliability. But also with multi-core, you get parallelism. So they're all connected. And these were three people who, whilst working independently of each other, came out with very, very similar conclusions.
Yeah, I met Carl Hewitt, 3 years ago now, and I was talking with him about the actor model. I mentioned we implemented the actor model, but we didn't have a goal of doing this. In fact, I didn't even know about the actor model until later I read reports, blogs saying Erlang implemented the actor model. So I had to go and find out what it was. But he saw this as very positive, because they had worked from the actor model from a more theoretical point of view. We'd worked from an extremely pragmatic point of view and arrived at something very close. So he saw this as a strength of the actor model itself. We came to the same thing from both sides.
Yeah. And you can find this interview on YouTube. Just search on hashtag talk concurrency, and it comes up. Yeah. So.
Yeah, this is concurrency. We separate concurrency and parallelism. We see these as two different things. In many places, you'll see people equate these. You read a paper about concurrency, and they're talking about parallelism, and the other way around. We separate these things. So concurrency, that's about doing lots of things at the same time. Okay. Again, this quote is from Rob Pike, whereas parallelism is doing lots of things at once. And they're two separate things when you start thinking about it, really. They interact perhaps, but they're not exactly the same thing. So here, very simple, concurrency versus parallelism. Here we have two tasks, A and B. Now A is going to do A1, A2, A3, and B is going to do B1, B2, B3. What we can do, we can run these concurrently, which you see on the upper one here, on one thread. So this thread is doing some A, then it's doing some B, then it's doing some A, then it's doing some B, etc., doing these. So here, we're running these A and B here concurrently, but not in parallel. Down here, we have two threads, or two processes, or however you want to view it. And here, one is running A and one is running B, and now we're running them in parallel. And they're not the same thing. What Erlang gives you is a concurrency model. It gives you concurrency. I can start up 100,000 processes, 1 million processes, and it will run these processes concurrently, and it will use the underlying parallelism in the system. This is what Francesco was in. If I've got a 10-core machine, like that one is, it will run 10 things in parallel. I don't see this when I'm running it. I'm programming concurrently. If I'm running on a single core, just run them singly. I won't notice this in my program.
How many of you have a bed from IKEA? A few of you do. Okay. So if you were to assemble that bed, assume you buy 2 beds. If you were to assemble your beds concurrently, you'd take your partner, one of you would do one bed, the other would do the other bed. If you were to do it using parallelism, you would both first work on the first bed, get it finished, and when you're done, you'd go in and assemble the second bed. So I think that's the main difference. So concurrency is basically built on top of parallelism, and it makes it appear like, concurrency makes it appear like things are happening at the same time. You just model it that way, whilst parallelism actually makes sure that they do happen at the same time. So it's a way of modeling versus a way of executing.
So I see concurrency as a property of the problem and of the solution to that problem, and parallelism as a property of the system you're running on.
So yeah.
That's how my view of it here.
And I mean, how so we've been talking about Erlang. I think a lot of it is built around the Beam, the virtual machine, and I think the Beam and the JVM, I think more or less, were born at the same time. Development on them started more or less at the same time. And I was at the computer science lab back in the mid-90s with Robert, and one of my colleagues, I think it was Klacke, came up and put the Java white paper on my desk. And I had a sense of deja vu. It was a concurrency model. It was green threads at the time, so it was lightweight processes. It was a garbage collector, built-in memory management. And and it's been interesting to see the JVM and the Beam take very different routes. And there are lots of talks comparing the JVM and the Beam. But I would say there are three major differences when we look at them. The JVM is built with threads and versus concurrency. The Erlang is built, the Beam is built for concurrency. You've got shared memory versus no shared memory, and mutable state versus immutable state. And the concurrency based on shared memory will mean stop the world garbage collector. And it also means it's harder to use your code base for distributed programming, because you need to deal with the shared memory. You need to deal with libraries which have the shared memory. And the location of the memory always becomes a sticking point. And I tend to say, when I compare and contrast them, is that the JVM was built for speed and parallelism, and the Beam was built for scale and resilience. And it doesn't say that you can't do one with the other, but that was very much, I think, the focus as they were working on it. And yeah, if you look at the JVM world, I think the power of concurrency got added through Akka. Right before this talk, on top of Akka, Martin introduced, mentioned Calyx, which again are similar ideas which we've had ourselves. And what happened is, what Jonas Bonnaire did when he created Akka is he took ideas from Erlang and implemented them on top of the JVM. And I'm happy to have Martin Thompson sitting in the first row here today. But you go in and find any of his talks on YouTube. And what he will do is he will be describing, at least in my eyes, what we're talking about today. But he takes the ideas of what we're talking about today, and he uses and implements them on the JVM to get this amazing speed. And what has this?
Yeah, no. Go.
Oh, okay.
Far away. Yeah.
What has this concurrency model led us to? This is a blog post from WhatsApp from 2012, and back in the early days of WhatsApp, we were meeting with the founders, Jan and Brian, in cafes in downtown Palo Alto. Because, they didn't even have an office, and since day one, I think one of their goals was to actually reduce operational overhead and hardware costs. This was even before they had their A series. That they were still. It was still very, very early days, and they really wanted to try to pack as many users as possible on a single machine, to reduce the actual costs. And they did that by maximizing the concurrency on both the Beam and being able to handle an amount of users which were able to connect simultaneously through sockets. And what they did is, in 2012, January 2012, they managed to achieve, by hacking FreeBSD and doing minor changes on the Beam virtual machine, 2 million TCP/IP connections. And and how they did it, they did concurrently at the same time. So this was 10 years ago. So that was pretty impressive back then. But of course, there were changes in FreeBSD, there were changes in the Beam. Yeah.
But they were quite minor. I was talking to one of them later on in 2012, and he said occasionally they would peak at 3 million concurrent connections. Now, from my point of view, running 3 million processes in Erlang is trivial. How do you get 3 million TCP connections into one machine? That's the difficult bit, right? But, I don't know how they did that. But
and that's exactly the problem they found a few years later, 2015. So Phoenix, I don't know how many of you here have heard of Phoenix, but it's, a few of you have, yeah. It's a modern day Ruby on Rails. It's written in Elixir, and it runs on the Beam, so it's part of this ecosystem. And the changes WhatsApp did in 2011 on the Beam, VM, and FreeBSD, it took a few years, but they all trickled down to kind of mainstream operating systems, as well as the Beam itself. A lot of those changes were eventually merged. And so 3 years later, running on an AWS instance, they were able, using Phoenix, they were able to open up 2 million socket connections, so WebSocket connections, and keep them open in a very, very stable way. And they actually even mentioned, if you scroll down in the blog post, that they could have gone further. They weren't utilizing all of the CPU, they weren't utilizing all of the memory. And what was actually blocking them was opening up, what was the network, which AWS was basically limiting them on. And I think this is the blog post which turned Elixir into a first-class citizen of the Beam, but it's also what made me realize that all of a sudden a programming language had become an ecosystem of programming languages.
Yeah, so from my point of view, I don't see Erlang as a language with concurrency. I see it as a system with a language on top of it. In this case, what's happened now, of course, there are many languages there for it. But when you look at systems written on top in Erlang, on top of Erlang, you'll find they're very much operating system-like. They seldom have a central thread of execution. They'll be doing lots of different things at the same time. I'm running my web server, I can open up a browser, and I can run in that, and I can open up a shell from the Elixir or Erlang system on that, just like a normal operating system. And what's happened now is that there have come a lot of other languages implemented on top of the Beam, and they all inherit all the basic properties they get from Erlang. So here, well, Caramel, Gleam, that's static experiments so far on statically typed languages. We haven't mentioned it, but Erlang is dynamically typed.
Fez and Alpaca as well. I mean, yeah.
Fez, talk over there.
If you're curious about F# on the Beam, yeah, that's the person to speak to.
Yeah.
Call you Nielsen right here. So yeah, it's and it's interesting to see all of these experiments happening.
Oh, yeah,
It's I mean, Robert started off with this flavored Erlang and
parentheses rule. Yes. Parentheses rule. That's it, right?
There are I think 2 or 3 Prolog implementations on the Beam. There was a C-like implementation, FN, which I think was the first language ever written on the Beam in 2008.
Yeah, it was sort of Python inspired.
Yeah.
It wasn't Python, but it is Python inspired in many ways for it.
And yeah, LuErl and many, many others. But obviously the largest one today, without doubt, is Elixir.
Yeah.
And why is that? Why is kind of Elixir now becoming much, much larger? And it's interesting, again, it boils down to what problem you're trying to solve. When Robert, Mike, and Joe started off, they were trying to figure out how to program the next generation of telecom switches. And that's the problem they solved. You go in and you ask Jose Valin, the creator of Elixir, what problem was he trying to solve? And he'll tell you he's trying to bring the power of Erlang to new communities. And in doing so, you want to start with the web, followed by embedded. And now keep an eye out over what's happening in the machine learning space. There's a new framework called Axon, which they're looking at ensuring that you've got the same level of accessibility and ease of use as you have in the web space, but also in the embedded space. Yeah. So Jose Valin's focus had not been on solving problems, but on the adoption of a solid runtime and language principles, through good frameworks, accessibility, and really top and high-end documentation.
I can say one thing, I was extremely surprised. What Francesco was saying, we were out to solve a problem, and then I heard that someone written a web browser or web server in Erlang. I thought, why would anyone want to do that, right? It was just weird, because that's not what we were thinking about. When you start looking at the problems, you'll find they're very, very similar, in many cases, very similar type of things they're after. They want to run massive things at the same time. You don't want your server to crash, right? If I've got a company with a web server and it crashes, that just gives the companies a bad name. So you might lose connections, but the server should keep running. You want to keep it running the whole time and things like this for it. So there are very many cases. The properties they want to handle are the same. Right? That's why it works in that sense as well.
And I think the interesting part, again, a web server. I mean, this was. I recall that web server. Yeah. I was actually using it and playing with it back in '95. But if you go in and look at some of the benchmarks they had with yours, which is yet another web server which came around was open sourced from Nortel Networks in 2000, 2001. That server completely trashed Apache, and it managed to handle probably 70,000 simultaneously open TCP/IP connections, when those benchmarks were made, whilst Apache was still kind of hovering at 7,000-8,000, with no degradation of throughput and service. But no one thought of packaging it up as a standalone application, similar to what they've done, for example, with RabbitMQ. Because again, that's not what we were doing. We would take probably what was one of the fastest web servers available at the time, and we'd embed it and use it to serve pages to operational team, telling them that their system was down. So and again, because it's depends from what angle you're coming from and what types of problems you have to solve. But I think Jose really did the right thing, putting in a Ruby-like syntax to Elixir, because there's not much Ruby in Elixir, but apart from the syntax, but it opens up the doors, and with a sense of familiarity, and it reduces the psychological barrier to entry. He added macros, kind of inspired from Clojure, again, to create a dynamic language which could easily be adapted and changed for different use cases as well. And we had that. I mean, we had macros in Erlang as well, but we made sure that they were very, very hard to use, because, we were discouraging people from using them. Because maintainability becomes a nightmare, and I think that was one of the key concerns we always had.
The Erlang macros are very primitive, and they're not going to change. They haven't changed in 30 years, they're not going to change now. So.
No. And I think, it's going to be really interesting to see what the next language is, And where we're today is one of the areas which I think we've been strong in is around orchestration. And I think even there, the whole semantics of a language and the distribution which is built in allows nodes in your cluster to come and go dynamically without having to change your code base or having to worry about any of that. And again, this is happening today with containerization and Kubernetes, where you can spin off containers and tear them down. So it's fairly straightforward. So it's the big challenge we have now is the overlap of functionality. What functionality is provided by Kubernetes versus the ecosystem, and how do you convince a DevOps team who doesn't know anything about Elixir or Erlang not to utilize features in Kubernetes when they already exist in the ecosystem, because that's when you then end up getting a lock-in in a particular tool, which you want to go in and try to avoid.
Oh, well, this is just me. Yes, so, I don't know, there is a quote by a guy called Greenspun, and I have to get the quote here right. It is his 10th rule of programming. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. There is no rule, he doesn't have a rule 1 to 9. The 10th rule for it, but I thought this was quite funny, and I'm a Lisper, so of course I assume I know it's correct, right, for it. But this would actually migrate quite well over into Erlang, in the fact that any sufficiently complicated concurrent program in another language contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Erlang, because you're attacking exactly the same problems, right? That's what you're doing. That's with the same properties. That's where you end up. And the fact that Erlang does it at a very low level at the base of the system means they can be extremely efficiently done. They are extremely efficiently done, because it is at the low level, and you build your language and stuff on top of it. And this is, yes, I thought that was very funny.
So, I mean, the point is, it is very, very hard, if not impossible, to bolt on a concurrency model to a language as an afterthought. It is something which you need to think about from the start, because not only does it go in and affect your whole runtime environment, it will actually even affect how you code in that particular language. And I think it's going to be very, very, very interesting. I think we come to conferences to learn. One of the things I learned from this conference is that they recently added concurrency to Swift. And I think it's going to be interesting to see if it works out, because right now you've got a whole community of developers used to doing things in a particular way, and migrating the mindset to using concurrency as the key building block will probably not be easy. Not only how do you go in and actually use the library, so it's something which needs to be part of the language from day one.
I can just continue what Francesco is saying. If you're coming into these languages, it is a big rethink on how do I structure my system? How do I structure? What do I need to take care of? What can I let the underlying system take care of for me? How do I use the best things for it? I mean, we have these things for handling errors. How do I use those in a very nice way to get the right functionality I want in a good way? And that can be quite a large rethink on how I structure my system for it. So it's not always trivial to do it, but once you get in there, do it. And like the let it crash philosophy, that feels very bad, right? If something goes wrong, why should I crash the process? Because that can do an awful lot of stuff, right? Make things very much worse. Of course, from the Erlang point of view, we're letting one Erlang process crash. We're not talking about the Erlang system crashing. I can just have one very funny thing I read. Stack Overflow, a number of years ago, they were discussing the let it crash philosophy in Erlang. And one guy was getting very worked up about this. So he said, how can you just let things crash? If my systems crash, it's going to cost me a few $100,000 every time, right? So I cannot let it crash. Of course, what no one had explained to him, we're not talking about the whole system crashing. We're talking about tiny chunks inside the system crashing. And the system designed in such a way, it can handle this, keep on going, restart when necessary, and not crash. It's very hard to crash an Erlang system, unless you know what you're doing and you know how the system's designed, right?
And the whole let it crash doesn't mean you're not ignoring your errors. You're just taking care of your errors in a slightly different way, in a way which is standardized from across the board. And so by letting a process crash, you're handling software errors, you're handling corrupt data errors, you're handling network errors, you're handling distributed programming errors. So basically what happens if your remote machine crashes, what happens if your remote container crashes, what if the VM crashes, what happens if the answer is lost. So you all handle all of those things which can happen in exactly the same way and in a consistent way across programs. Yeah.
There's one error we can't handle. If the machine itself crashes, that we can't do much about, I'm afraid. But that's about it, right?
But that's why you have two machines.
That's why I have two. Yes, if you want to make a truly fault-tolerant system, you have to have at least two machines. Preferably, they should be far away as well, too, so if the power goes at one, it doesn't go from both of them. But okay, we're not going to get further into that, yes.
All right. Thank you for having us. Thank you for coming.